Yeah, thanks a lot, Mark, for the kind introduction and to all the organizers for inviting me. And first of all, I have to apologize. This seminar was supposed to be months earlier, but then other things came into the way, in particular our Nordita program, and then was just a little bit too busy. Also, I'm sorry for delaying a little bit. I just came out of tutorium, so it was a bit tight today. Good, with this out of the way, thanks all for coming. Would like to talk about this paper with this very short title that Mark already told you. Paper with Alessia about positivity bounds, weak gravity conjecture, and landscapes. So maybe I want to start with some general remarks. Namely, this talk is about, was kind of motivated, and this paper is motivated by thinking about predictions in quantum gravity. So more precisely, the question, what is the set of predictions that we can make from asymptotic safety? And here are some remarks. First of all, the first remark is that predictions have to be read off at k equals 0, where k is the FRG scale. You cannot really read off the physics at finite k or k to infinity. So we really have to integrate out the whole flow and then read off the physics, because this is the effective action. Very straightforward comment, but it's still important to make this comment. The second comment that I want to make is that in general, we have more than one relevant parameter at UV fixed point. So really, we will in general not have a single prediction or like a single set of predictions, but there will be a landscape of predictions. So different predictions depending on how you change your relevant parameters. So how you flow out of your UV fixed point. Now, one question that has been asked more recently, or has received more attention recently, is that within asymptotic safety, there are, of course, some questions beyond the existence of the UV fixed point. Namely, for example, how do we check the unitarity or the causality of the theory? And we address this from somewhat new perspective here. And then also another question that kind of motivates this work is, how do we compare with or to other theories of quantum gravity? So these are the main motivations to look into this, at least from my personal perspective. Maybe Alessia differs in her motivation. So this is the outline of my talk. I will first talk a little bit about landscapes in quantum gravity, and then about positivity bounds and swampland conjecture. So that's kind of the first part of the very long title. And then in the second or main part of the talk, I will talk about a specific landscape that we computed in asymptotic safety related to an abelian gauge gravity system, and then wrap up with a summary. Okay, so let's get started. What do I mean by landscapes? And landscapes has, of course, well-defined meaning that I'm trying to work towards a little bit now. So let me just plainly define what I mean by landscape. By landscape, I mean the following thing. Consider effective field theories, EFTs, of just matter, so without gravity, so valid in the infrared. And I'm asking myself the questions, which of these EFTs admits a UV completion when I couple gravity to it? And those that admit such a UV completion with gravity, I call that they are in the landscape. And those that are outside of the set, so those who do not have a UV completion in the presence of gravity, belong to the so-called swampland. And here, let me be very precise, I do not refer to any specific theory of quantum gravity or specific UV completion. For now, I want to define these two concepts just as really general. So that's what I just said. A priori, there's no reference to, for example, string theory, even though this whole idea kind of comes from this community, you could say. And many of the investigations of the swampland or landscape, or however you want to call it, have been done in the context or somewhat related to string theory, I would say. Okay, and then you can ask several questions about this. Of course, the first question that pops into mind is that maybe if you do have different UV completions or quantum gravities or however you want to call it, do they have different landscapes? And this question has been asked before, for example, in these two papers. And especially in the second paper, there was also some notions introduced, like the absolute swampland. So this is what I here plainly call swampland, as the set of EFTs that simply do not admit any UV completion whatsoever. Okay, so in a picture, if you want, take asymptotic safety as one potential UV completion and string theory as another. This is what we have in mind here. So you have the UV completion as this dot at the top of the plot, and then different IR predictions for potential EFTs that can come out of the theories. And then let's not worry about the positivity bounds for now, but you can derive an asymptotic safety landscape from the fixed point of asymptotic safety, and you can derive a string landscape, at least in principle, from string theory. And the question is, do these landscapes intersect? Are they the same? Do they not intersect? So what is their relation as sets of EFTs, if you want? So this is one of the questions that we have. Okay. But now you can ask the question, right, this is all well and good, but how do we operationally define a landscape, right? This was kind of abstract in a sense, this notion. Operationally, how do we make progress here? How do we compute something? And asymptotic safety, we are in a very fortunate situation, if you want. We can perform actual computations here. And my operational definition of the landscape, at least for asymptotic safety, but I think it's valid more generally, is simply a unique specification of all the EFTs inside, right? Well, the EFTs we can specify by dimensionless Wilson coefficients. So if you want, these are the couplings in the effective action at k equals 0. But of course, now not all of them, because we have this distinction between essential and inessential couplings. In general, we can do field redefinitions, so not all the couplings that you can write down are really appearing by themselves in, let's say, a scattering amplitude or something like that. Why do I say dimensionless ratios? Well, this is important because in gravity, we always have a Planck mass or Newton's constant, if you want. So we have a dimension for scale. And you can, of course, set this scale once and for all. And then all the remaining couplings that can appear, you can phrase in terms of dimensionless ratios. And this specifies the EFT uniquely. So on the following, I will just look at dimensionless ratios. Good. Now there's a very well-known trivial landscape that has been computed in asymptotic safety, or at least part of it, namely the product of G and lambda. This is a dimensionless, coupling, right? And depending on your flavor of implementation, certainly this includes all the negative real line. But if we believe that this lambda equal 1/2 pole is really an off-shell pole and on-shell everything goes through, as some computations show, then really for us, the product of G and lambda can span the whole real line. But of course, if you want to compute larger parts of the landscape, you want to know more of the EFTs, right? You want to have knowledge, especially about the irrelevant operators, because they are the predictions of the theory. We have to go beyond simple truncations like the ancient Hilbert truncation. Once again, I want to stress that you need to take the limit k to 0 to talk about the landscape, because by definition, once again, these are the EFTs that we are looking at. So effective actions, not average effective actions. So we have to take this limit k to 0. We have to integrate all the way down. Okay. Once again, in a picture, how does it look like in asymptotic safety? in the center, you find this UV fixed point, and then a few, let's say, greenish trajectories that emanate from this fixed point, and then the landscape that is traced out by all potential IR limits that stem from this UV fixed point. And this is this purple line that is the asymptotic landscape, asymptotic safety landscape attached to this fixed point. And of course, there's also other trajectories, these unsafe trajectories that do not emanate from the UV fixed point. But these could, for example, stem from, let's say, string theory, UV completion, and they could form their own landscape, but they need not to. Okay. So this is a very, well, bird's eye view, if you want, of landscapes, and don't want to go too much into more detail here. But now continue towards positivity bounds and swampland conjectures as the second ingredient that kind of motivates this whole study that we did. So let me start with positivity bounds. Once again, I want to be at a rather superficial level here and just want to give you the main idea behind it. And the core idea is that, well, you're in an EFT setting, first of all, and you have physical requirements of your theory. That includes, for example, unitarity, causality, maybe some more properties that you want. And if you take these physical requirements, these imply mathematical conditions on scattering amplitudes. For example, analyticity in the complex plane. If you think of a 2-to-2 scattering, analyticity in the Mandelstam variables ST and U. Now the point is, well, we can compute scattering amplitudes in the EFT. By EFT here, I really mean we've integrated out some heavy physics and we are looking at the light physics. And what is done in practice is, once again, I don't want to describe all the details. There's a lot of literature on that. The gist is you consider a specific contour integral that defines derivatives of the amplitude at zero energy. And you can actually put constraints on these derivatives by these mathematical conditions that, once again, go back to physical requirements. And this way, the punchline is that you can derive bounds on the couplings from this infrared EFT. And in that way, you can kind of indirectly put constraints on your UV physics, because, again, if you think of asymptotic safety or really any UV completion, you run down the RG flow, and you get results for your infrared couplings, your EFT couplings. But especially in asymptotic safety, we are maybe not yet sure that we fulfill unitarity and causality. And now if I find that positivity bounds are violated, this gives you a first hint that maybe the fixed point that you started with is not unitary. So in this way, we can use somewhat well-established EFT technology to learn more about the asymptotic safety fixed point. Okay, so much for the positivity bounds. The second thing that I now discuss is the swampland conjectures. And let me maybe a bit provocatively define swampland conjectures as guesses, and the adjective ranges from educated to wild, depending on the conjecture. So educated or wild guesses, and on which theories belong to the swampland and which belong to potentially a landscape. Now, once again, this whole idea stems from a string view, if you want, a string theory as a motivation. There's string inspired, most of them. And there's definitely an open question on how universal some of them are. But on the other hand, let me also say that some others, that's where the educated bit comes from, can actually be derived from positivity conservatives, so these positivity bounds. So in that sense, they're pretty much established in a sense as far as you can get, really. So for one example would be this weak gravity conjecture. You can, of course, make an argument from black hole physics, but you can also derive a positivity bound that gives you one version of this weak gravity conjecture, just from these general requirements on an EFT or on the physical theory. specifically, this would be one such positivity bound. What I have in mind here is a gravitational theory with higher order terms like Ricci squared, Riemann squared couplings. And then I'm looking at a charged black hole. So this psi parameter tells you about the charge over mass ratio, and it varies between 0 and 1. And if you derive the positivity bound in such a setup, you get this relation for the two couplings that are in front of the Ricci squared and the Riemann squared term. This positivity bound should be valid for all values of xi between 0 and 1. So something like this you should have in mind if I'm talking about positivity bounds. Okay, now with these general concepts out of the way, these are the things that we wanted to investigate in an asymptotic safety context. So, and what we took as a specific example is in a billion gauge theory. So if you want a photon coupled to gravity. So now a bit more technical part of the talk starts, but I think it's interesting, but we still have to go through some technicalities. In one bullet point, for the experts in computation, what we do is a fourth order derivative expansion with a minimal essential scheme, harmonic gauge, and the dim regulator. If you're not into the computations too much, doesn't really matter. Maybe the more important thing is this is the action that we look at. So we have an Einstein-Hilbert term. We have the second term is the Euler term. That's not really that important. I will not discuss it. We discuss it in the paper, but I don't want to pay attention on it too much in this talk. This F2 is the kinetic term for the photon. And then we have self-interactions for the photon. So a kinetic term squared, this is this F2 squared. And then an F to the 4 term, which is this F4. And then there's one non-minimal interaction. That's the Weyl tensor C contracted with two field strength tensors. That's the last term. As I kind of alluded to already, we do perform a field redefinition in the sense of Baldacci, Aizinati, and Falls to remove all the other terms consistently. So you could write down, for example, in a term Ricci scalar times f squared or Ricci squared. These can all be removed within the minimal essential scheme. So this basis that I've written down for you is really the complete basis of essential couplings. And in going forward, it actually turns out that this original choice of couplings, so this GF2 squared and GF4, is not the most convenient one, but we rather use a G plus minus that I've defined here on the right. So we take the sum or the difference of these two couplings. And you will see the reason for this in a few minutes. So that's the setup. Let me dive into the fixed point structure that we derived from this. There are four interesting fixed points. There's, of course, the Gaussian fixed point, GFP, that's the first line. There's what we might call meta fixed point, MFP, where gravity is switched off, as you can see by the first column. So that's Newton's coupling. And then there are two interacting fixed points where both the photon has a self-interaction, but also gravity is turned on. This is FP1 and FP2. And so you can see the fixed point values of all these essential couplings. So this plus minus combination of the F2 squared and F2 coupling, and this non-minimal interaction of the CFF. And the last column is just the critical exponents. So as expected at the Gaussian fixed point, we only get negative directions. And then both the meta fixed point and this FP1 have one relevant direction. So they have one positive critical exponent. And then this FP2 kind of sits in the middle if you want, and it has two relevant directions. Structurally, if you look at this system, it is very similar to the same system where you've replaced the photon by a shift symmetric scalar that I investigated in essentially the same technical setup roughly 2 years ago. But of course, there's a bit of a longer story here. in this follow-up paper of Gustavo and Mark, we kind of found out that the corresponding matter fixed point is potentially not so trustworthy, and then as a consequence, also the corresponding FP2 is maybe not there, but it's it's not really obvious. But then there's some more recent work by Holger Gies and his student, also in connection to the Nijmegen group, that investigated also this photon system, just photon self-interactions, and they see something interesting there. I still want to understand this, so I would not right away conclude from our work from the shift symmetric scalar system that this FP2 and the matter fixed point are unphysical. So certainly one has to understand a little bit more here. So for this talk, I would just assume that all of these fixed points are, for now, considered interesting. Let me also say that there are more fixed points that you can find in the system, but as far as we can tell, all of them are shielded from the Gaussian fixed point by singularities of the flow. So really the interesting region, as far as we can tell, once again, is the set of 4 fixed points. Now, of course, the qualification, as far as we can tell, comes from the fact that we are talking about 4 couplings, and it's really already very difficult to find all fixed, to make sure that you've found all fixed points in the system. Okay, last thing that I want to point out here, specifically for this fixed point 2, have a look at the relevant critical exponents. So the most relevant is roughly 2, and then the second relevant critical exponent is 0.2. So there's 1 order of magnitude difference, and let me just say that numerically it was really a pain to get a good set of trajectories out of this fixed point. Okay, now let me say a little bit about the Wilson coefficients in the system before I show you the results on that. So as I've told you in the introductory part, we want to define independent dimensionless Wilson coefficients for our system. So these are dimensionless ratios of couplings. So what I will use is we use Newton's coupling to set the scale, and then the 3 other couplings, G plus, G minus, and this G CFF, in units of the Planck mass to define 3 independent Wilson coefficients. Okay, so I call these Wilson coefficients small w. So w plus minus is just the limit k going to 0 of the ratio. That is dimensionless, and the same thing for this WC. Now, there's a caveat here. They are infrared logarithms, right? So we have a photon that is massless, we have a graviton that is massless. So generally, you will expect logarithmic running for dimensionless quantities. As it turns out, you could expect that this is the case for all 3 of these Wilson coefficients. But it turns out that only one of these 3 shows a logarithmic running as k goes to 0. And this is this W minus. And this is now the justification that we've introduced the G plus and G minus. This is just to really put all the logarithmic running into one of the 2 couplings. So to define now the Wilson coefficient, subtract the corresponding logarithm, which is negative in this case for this G minus. So I add this term, this logarithm, to cancel it. And now W plus, W minus, and WC will all be finite when I take the limit k to 0. There's an ambiguity here, of course, namely, what is the numeric prefactor that I put into this logarithm? And there's a whole discussion to be had here. Let me just cut this short for this talk by saying that this is the choice that we've taken. And if you don't go too crazy, the results are stable qualitatively. But there's certainly more to discuss with respect to this. Good. So let me now tell you about the landscape that originates from this first non-trivial fixed point, FP1. Just to remind you, this is the fixed point with one relevant direction. So it has a single relevant direction, but the single relevant direction sets the scale. Okay, so really you don't have three dimensionless parameters. So the relevant direction is just used to kind of set the scale, so the Newton's coupling, if you want, in units of your k. So there's a single trajectory which emanates from fixed point 1 and goes all the way to the Gaussian fixed point. This is displayed here in this graph. So you have the four couplings, Newton's coupling, G plus G minus, and GCFF, going from FP1 to GFP. And as you can see, well, pretty standard plot for such trajectories. You have the fixed point regime that starts at roughly, well, in this case, 10 times the Planck mass. And then you bend over into infrared scaling. Okay, and since this is a single trajectory, I can just give you numerically the Wilson coefficients that are attached to this fixed point. So the landscape of this fixed point is a single point, and it's the EFT corresponding to these three values for the Wilson coefficients that we have access to. Okay. Now, what with the landscape of fixed point 2? To remind you, we now have two relevant directions. Once again, one is used to set the free parameter. So really you have a degree of freedom, if you want, of an angle. So we expect that the landscape that originates from this fixed point is a line. And indeed, we find a line. So what you can see now is the three-dimensional plot of the landscape that emanates from this fixed point 2 in terms of these three Wilson coefficients, W plus minus and WC. Yeah, so these are three different views on the same thing. I hope you get somewhat of an idea how this looks like. And it turns out that this whole landscape essentially lies on a plane. I'll come to this point in a second again. So but just to illustrate that a little bit, now in the second set of plots, you see a projection of this whole thing onto WC is 0. So just in the plane W plus and W minus. And you see the landscape is this somewhat bent line. Looks like a candy cane, right? So we looked at this and said, yeah, this is a candy cane. Somewhat funny, but okay. This is the landscape that you simply get out of this. Let me maybe add at this point that all the purple dots in this landscape plot correspond to the landscape of fixed point 2, whereas this red plot that you find at the tip of this candy cane, or the curved bit of the candy cane, is the single landscape point of fixed point 1. And it looks as if they are connected, and indeed they are, because there's actually a separatrix connecting fixed point 1 and fixed point 2. So you expect that the landscapes of these two fixed points actually connect smoothly. Now, we've learned actually some, as a short side remark, we learned some important nomenclature that maybe as a non-native English speaker, I can teach you something. So there are actually words for the two different parts of this candy cane. This curved bit is the warble, and the elongated straight bit is called the scrape. And if I don't mess it up, I will use these two words to refer to these different regions of the landscape. Once again, coming back to this difference of critical exponents, one roughly 2, the other roughly 0.2, it was really a numerical nightmare to get this landscape. So we're talking really about using, I think, 128 digits and differences in angle of 10 to the minus 15 to get individual dots on in this plot. So even though these dots in these plots seem to be quite far apart, the starting condition close to the fixed point is extremely close. So numerically, this was really a huge effort. Okay, as I've already mentioned, this landscape that comes from the fixed point 2 lies approximately on a plane, and it's parameterized in this way. So this is just a fit that we did, and this is what comes out. That's pretty remarkable already. The second thing that we noticed is that the straight bit, so this the straight part of the candy cane, is really pretty straight. So asymptotically, W minus and W plus have a linear relation. Then there's a subleading bit that has a square root and a constant. And this is interesting because you would not generally expect that a landscape like this has any particular shape. And in particular, it's not clear at all why this should be the case, why it should be essentially flat, except for this small wobble thing. So a question that we do not have yet an answer to, it's at this point just an observation, is whether this is a bug or a feature. Good. Last but not least, we also have this meta-fixed point, MFP, just to complete the discussion of the whole landscape of the system. Once again, we only have one relevant parameter, so at the fixed point. So effectively, we have 0 free parameters because one of them sets the scale. Now, the point of the MFP is that gravity is turned off, so we cannot use Newton's coupling to set the scale. So we'll use one of the other dimensional couplings to actually set the scale, and then we are left with 2 Wilson coefficients, so two dimensionless ratios that we can predict uniquely. And once again, here there's a very interesting observation. I'm not really sure whether symmetry is really the right term for this, but there's an exact relation between 2 couplings along the whole trajectory. So the observation is that G minus and G plus are related by a constant factor. Once again, along the whole trajectory that connects the meta-fixed point to the Gaussian fixed point. And it's pretty remarkable in my opinion. As I said, I do not really understand why this is the case. It might well be a truncation artifact, but this is what comes out. So if you want, one of the 2 non-trivial Wilson coefficients, I can give you an exact number for this within the truncation. So of course there's a truncation error, but neglecting truncation errors, this is the exact Wilson coefficient in the system. The second Wilson coefficient that you can compute, we couldn't compute analytically, but numerically at least, and it has this value. Minus sign is simply because this G plus has a negative value. Okay. So I should say that you could wonder whether the meta-fixed point is maybe, or this landscape is connected to the landscape of the other 2 fixed points, and you might expect so. And indeed, we find that this single point looks like a reasonable endpoint of this scrape bit that we found from fixed point 2. So within our numerical accuracy, and as far as we could compute data points, we get that this is really the endpoint of the scrape, even from extrapolating just the scrape. Okay, so far this is all the analysis that we did from the, if you want, pure FRG perspective, and things that you can compute in the infrared. Now let me come to these positivity bounds that we want to investigate, and we simply took them from the literature. So there's a list of positivity bounds that we found. So positivity bounds 1, 2, and 3. There's something called the entropy bound, and then the weak gravity conjecture, which is a special case of this. Don't worry about the details too much. The important thing is that, once again, these can be derived on very solid grounds, simply from EFT considerations and imposing unitarity, causality, Poincare symmetry, and so on. So relatively reasonable assumptions, I would say. And the question now is whether our landscape that we computed from these fixed points fulfills these bounds or not. And in a word, no. Very bluntly, we are not quite fulfilling these bounds, but let me show you the plot here. What we are plotting is, again, the kind of projection onto WC is 0, because that's a pretty good approximation. And what you see, once again, is the landscape, or these purple dots and the red dot, the candy cane is our landscape. And the green and blue regions are where these positivity bounds are fulfilled. So you see that this whole candy cane region lies to the left and outside of where the positivity bounds apply. Okay, so what does that mean? Positivity bounds are not fulfilled. Is asymptotic safety dead? Do we now all convert to string theory? Well, not so fast, right? So there are some qualifiers here. The first is very important, I think. Well, both of them are very important, but first is conceptually important, namely that you have to ask the question, where are these bounds coming from? And the bounds have been formulated for an EFT where massive degrees of freedom were integrated out. And this does not really apply to our situation in full glory, if you want, because we are also, well, we are only integrating out massive degrees of freedom, right? We have the photon and we have the graviton, they are both massless. And in the presence of massless particles, you expect infrared divergences. So this is exactly this logarithmic running that we saw in one of the couplings. And there have been considerations of this part also in the literature, in the EFT literature, and the expectation is really that such soft violations as we see them are actually expected. So in our case, really these violations are Planck mass suppressed because we are forming dimensionless ratios of a coupling over Planck masses, right? So really the violations that we see are tiny if you compare them to violations that you could get from, let's say, electron fluctuations. So if you want to be more serious about this whole system, you would have to really add in an electron and then compare what the electron contribution to these Wilson coefficients would be compared to the slight violation. Okay, the second thing that I want to stress, of course, is that we have systematic uncertainties. And if you've happened to have checked the archive on the day when the paper came out, there was a second really nice paper on the very same topic. And of course, this was not a coincidence. And we look at the same system and we find slightly different results because we make slightly different approximations. And in this paper by Sean Peters and Schiffer, they find that positivity bounds are actually fulfilled. And if you also look once again at our results, we are pretty close to fulfillment of these positivity bounds. So at least to me, it doesn't look unreasonable that within systematic uncertainties, if you are more precise and include more operators, that you can, even with the caveats that I mentioned about where these bounds come from, even then you shift into this allowed region, if you want. Good. Another thing that you can look at to understand the system a little bit more is you check the positivity bounds along the flow. And this is really just to understand, like, what is the direction, if you want. So just do these, if these bounds would have to be fulfilled along the whole flow, does it get worse towards the infrared or does it get better? And here are 4 trajectories that we looked at that are representatives of the whole landscape. So on the top left, you see the single trajectory that emanates from FP1. So the one with the one relevant direction. And then the 3 other plots all correspond to trajectories stemming from this FP2 with 2 relevant directions. And then there's, on the top right, there's one that is coming from the straight part. On the bottom left, that's coming from somewhere in the wobble part. And then the bottom right is somewhere in this crossover regime. And if you look at the size of the violation in all of these plots, you see that as you go from the straight part towards the wobble and then finally end up at the tip, where you get into this fixed point one landscape, you violate these positivity bounds less and less. And generally close to this wobble part, you actually, going from UV to IR, you decrease the violation, whereas this is not the case in the straight part. And it's somewhere roughly equal in the crossover part. Okay, now this brings me already to my summary. What are the punchlines here? So the quantum gravity landscape is really, think of it as the space of possibilities. And in the space of possibilities, with asymptotic safety, we can make quantitative predictions on the landscape, right? I think that we are one of the few approaches to quantum gravity that can make such quantitative predictions. I think this connection to EFT considerations is helpful because it gives you additional information. It gives you an indirect handle on unitarity, causality, and so on. Because once again, if you really can show that you violate these positivity bounds, at least one of the assumptions that go into the positivity bounds has to be violated. And this, in my view, complements computations, for example, of the full propagator, of the graviton propagator. So this kind of gives a more complete view on what we really have in asymptotic safety. The current limitations are, of course, related to this infrared non-locality, the logarithmic running, and so on. We do not have a massive field yet, and then also systematic uncertainties. And with that, I'm at the end of my talk, and I would like to thank you for your attention.
All right. Thank you, Benjamin, for a very nice talk.